revision lecture on algebraic structure where we'll solve few problems. I hope you have already gone through the basic definition. So we'll begin with the examples. So the first question to begin with, Z plus is a group. So for a group, it must satisfy four properties. So closure, associative, identity, and inverse. So as you can see, Z is closed under this addition group. In other words, you pick any two integer n and m. When you perform the addition n plus m, it belongs to the integer set Z. This implies the addition is closed. The group is closed under the addition operation. Associative, you pick any three integers. You may perform n plus m first and then add with p, which will be same as you perform m plus p and then add with n. In both cases, you will see that the result is same. This is what associative property is. Next is identity. So identity is that element in the group which when operated, which when added with any other integer, it will give you the same integer. So the identity in this group is 0. So 0 is an integer and you pick any element from the integer n plus 0 or 0 plus n, both is going to give the same integer n. Inverse. So for given any integer n, what is the integer which when added with n gives identity element? So the integer is minus n. If n belongs to n, then minus n also belongs to n. And when you perform n plus minus of n or minus of n plus n, it is going to give you identity 0. This identity is called additive identity of Z. Let's go to the next example, Z plus plus. Does it form a group? So to solve this problem, some of you might argue that integer 2 does not have inverse minus 2 or integer 1 does not have minus 1. You should not argue like that. Before arguing anything related to inverse, first you must discuss about identity. Does it have identity? Without identity, you're not going to talk about inverse. So does it have identity? 0 does not belong to Z plus. So you're not going to talk about inverse at all. So since it does not have identity, it is not a group. Then what is it? It is simply semi-group. What is semi-group? Semi-group has closure property. Without closure property, you're not going to discuss any algebraic structure, as we have already discussed in the class. And second property in a semi-group is associative property. Next, R star with respect to multiplication. What is R star? You remove 0 from the real number. What is R star? You remove 0 from real number and all the remaining numbers belongs to R star. And with respect to multiplication, does it form a group? You can verify. Does it have a closure property? Multiply any two integer. What do you get? When multiply any two real number, any two non-zero real number, what do you get? Again, a real number for non-zero real number. What about the associative property? You are free to put bracket around these three variables and you see that the outcome is same. So associative property is satisfied. Next, identity. Which element when multiplied with any real number gives you the same real number? 1. So 1 is non-zero real number such that x multiplied with 1 or 1 multiplied with x is going to give you the same real number x. Next, inverse. So if x is your non-zero real number, then which real number belongs to R star such that when multiplied with x will give you identity element? What is the identity here? 1. And what it is called? Multiplicative identity. Multiplicative identity. In the previous example, we have seen identity. What is that called as? Additive identity. So inverse of x is x into 1 upon x, or 1 upon x into x. This is going to give you 1. So you see that every non-zero real number has inverse, and hence R star forms a group under this operation. Okay, so the first example and third example, which is a group, are infinite group. We also have a finite group which is represented as Z6 with respect to addition modulo 6. So Z6 with respect to addition modulo 6. Whenever you have a finite group, it is always better to use Cayley table, as it is going to answer so many questions simultaneously. So Cayley table for this Z6 will be plus 6, 0, 1, 2, 3, 4, 5. So the elements belonging to Z6 is 0 to 5. So you write in the same order in the rows and column as well. How do you get the entries of the Cayley table? You add the corresponding elements in the rows and columns, and you take the modulo 6. So 0 plus 0 is 0, modulo 6 is 0. 0 plus 1 is 1, modulo 6 is 1. 0 plus 2 is 2, modulo 6 is 2. By the way, what is modulo 6? When you divide the number by 6, the remainder is what you are going to get. 0 plus 3. So when you divide 3 by 6, what is the remainder? 3. 0 plus 4 is 4. 0 plus 5 is 5. Similarly, 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 3. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. 1 plus 5. 1 plus 5 is 6. What is 6 modulo 6? It is 0. In other word, you put the 6 here and you divide it by this. So 6 times 1 is going to give you 6, and the remainder is going to be 0. So here you will get the entry 0. Similarly, 2 plus 0, 2, 2 plus 1, 3, 2 plus 2, 4, 2 plus 3, 5, 2 plus 4 is 6, it is going to be 0. 2 plus 5 is 7. What is 7 modulo 6? When you divide 7 by 6, what are you going to get? As a remainder, 1. So you will write 1 here. 3 plus 0 is 3. 3 plus 1 is 4. 3 plus 2 is 5. 3 plus 3 is 6. Again 0. 3 plus 4 is 7, which is 1. 3 plus 5 is 8. So 8 divided by 6, the remainder you are going to get is 2. So you will write 2 here. Similarly, you can 8, 4, 5, 0, 1, 2, 3, and this one will be 5, 0, 1, 2, 3, 4. You can verify the remaining entries. Now, is this a group? First, closure property. What do you mean by closure property? By closure property means you pick any two element and perform the addition modulo 6, the operation given, binary operation given, and it will belong to the same set. So as you can see in the Cayley table, you have performed all the possible, you have picked all the possible pair and performed the given binary operation, and you see all the entries are between 0 to 6, 0 to 5 including. So this closure property is satisfied. Closure property is satisfied. Associative you cannot verify here. You need to verify it separately. Next, identity. Can you find any element which when operated with any other operand is going to give you the same element? So you see 0. 0 plus 0 is going to give you 0. 0 plus 1 going to give you 1. 0 plus 2 going to give 0. So first row and first column, you see 0 plus the element is the element plus 0 is the element. So 0 is your identity element. What about inverse? In any row, you see row number 1. Are you able to find 0? Yes. So what does this means? That 0 is the identity element. 1 and 5, they are inverse of each other. In other words, what element you add to 1 so that you get the identity 0? 5. What element you add to 5 to get identity 0? So you can see the row 5, 1. So this thing is going to give you the inverse. So the corresponding entry in the rows and columns is your inverse. So inverse of 0 is 0. So in all the cases, inverse of identity element is identity element in itself. Apart from that, inverse of 1 is 5, inverse of 2 is 4, uh, inverse of 3 is 3, inverse of 4 is 2, inverse of 5 is 1. So inverse is also satisfied. As for the associative property, in general, this is true. We have discussed in the class that x plus modulo 6y plus 6z, you can put bracket wherever you want. In other word, in other word, you add two number, take modulo 6, then you add with the third number, take modulo 6, or you add all the number at the same time, take modulo 6, or whichever way you want. This modulo operation is commutative over addition, so you are free to take modulo at any time. So next, is Z plus abelian? Yes, abelian. So first of all, whenever you are given such question in exam, before saying abelian, you have to ensure that it is a group first. If it is not a group, you are not talking about abelian group. So is it a abelian group? In other words, first you verify that it is a group. In previous slide, we have seen that Z plus is a group. So it is a group. We have to verify that. Apart from that, you have to show that pick any two number. So n plus m is same as m plus n. So this commutative property is satisfied, hence it is abelian. What about q star with with respect to multiplication? What is q star? Once again, it is a rational number from which you have removed the 0. So is it abelian? Before showing abelian, you have to verify that it is a group. So you have to verify it has a closure property, associative property, it has identity which is 1, it has inverse which is 1 upon x, just like a real number. And then you will show that multiplication of any two rational number is commutative, hence it is abelian. Is GLNR is abelian? This is also abelian. You can get the definition of GLNR from the lecture notes. It is a collection of all m by n by n matrices whose determinant is not equal to 0. That means it is a collection of invertible matrices. And next, given a subset, is it a subgroup of Z plus with respect to the same operation? So if you remember, if it is a subgroup, then it must satisfy all the four properties. However, there is a result which says you only need to show that the closure property and the existence of inverse. Rest all the properties is not necessary to show. So in case of 2z, you pick any two element, 2n plus 2m, you are getting 2n plus m. So it is element of 2z. So closure property is satisfied. You don't need to show associative property, and also you don't need to show that identity exists. It will exist if both properties are satisfied, closure and inverses. Given 2n, what is the number which you add and you get the identity? The number is minus 2n. You are getting 0. Minus 2n, you can add from left hand side also, 0. So inverse, existence of inverse is also satisfies. Showing this property is enough to claim that yes, it is a subgroup of Z. Similarly, for this case, since it is a finite element, it is always a good idea, good option to use Cayley table. So write the Cayley table for this subset 0 3, 0 plus 0 is 0, 0 plus 3 is 3, 3 plus 0 is 3, 3 plus 3 is 6. What is 6 modulo 6? 0. So you see that closure property is satisfied. What about the inverse? As for the inverse, inverse of 0 is 0, inverse of 3 is 3 itself, and hence it is a subgroup. Similarly, you can check for 1 minus 1 in this group, and this you can perform exercises at home. Now, as for the cyclic, if you remember, What is a cyclic group? It must have one generator. That means all the elements, you pick any element from the group, it must be generated by one element G. If it happens, it is a cyclic group. In case of Z plus, you see that if you have 1, all the elements can be generated using 1. For example, you take n. How will you generate n? 1 plus so on n times. What about minus n? Minus n can be generated as minus 1 plus minus 1, put bracket here, plus minus 1, so on, minus 1 n times. Okay, so some of you might get confused that here I have written g power I and here I am writing minus 1 plus minus 1. Do not get confused. Let me explain you. What does g power I means? G power I means g group operation, and group operation how many times? I times. So here you see what is the group operation here? Plus. So we are not writing g power I here. How we are writing it here? We are writing it like this. It is generated by 1. How we are generating it? Instead of writing g power I, we are writing k times 1, where k belongs to set of integers. So you have to be very careful. In the abstract definition, when you see, this is written as g power I, where I is taken from set of integers. In our case, we do not have g power I, we have I times g, where I is my k and g is my 1. So you have to be careful. So k can be negative, positive and everything, and hence 1 is able to generate all the elements. So can you find another generator for Z plus? The another generator is minus 1. So if minus 1 generates 1, then it will generate any other element. So how do you generate 1? Minus 1 into minus 1 will give you 1. Hence, it is able to generate all the elements. What about this finite group Z6? Again, go back to the previous Cali table, which we have just written. Can you find any row in which all the elements are covered? No. Can you find any element and track it down its power? For example, you track it down 1. 1. What is 1 plus 1? 2. What is 1 plus 1 plus 1? 3. What is 1 plus 1 plus 1? 4. What is 1 plus 1 plus 1 plus, and so on. So you see, it is going to give you all the elements. In other words, 1 is your generator. 1 is your generator. So you are going to get 1, 1 plus 1, which is 2, 1 plus 1 plus 1, which is 3, 1 plus 1 plus 1 plus 1, which is 4, 1 plus 1 plus 1 plus 1 plus 1 plus 1, which is 5, and then you have 1 plus 1 plus 1 plus 1 plus 1 plus 1, which is 6, and 6 is equivalent to 0. Let me erase this extra term here. 1, 2, 3, 4, 3, 4, 5 here. Okay. Is this the only generator? No. Any element which is co-prime with 6 is a generator of Z6. What do you mean by co-prime? The common factor of that number with 6 is only 1. There is no other common factor. So, which number is co-prime to 6? The other number is 5. In other words, what is GCD of 5 and 6? GCD of 5 and 6, 1. So 5 should be able to generate all the elements. You can verify. 5, what is 5 plus 5? It is equal to 10. What is 10 modulo 6? It is equal to 4. Once again, what is 4 plus 5? In other words, this is equivalent to 5 plus 5 plus 5. This is equal to 9. What is 9 modulo 6? 3. Next, 3 plus 5. What is this equivalent to? 5 adding 4 times. What is this equivalent to 8? What is 8 modulo 6? 2. Next, what is 2 plus 5? 7. What is 7 modulo 6? 1. Next, 1 plus 5, which is 6. What is 6 modulo 6? 0. So you see all these 6 elements are generated using 5. So 5 is also a generator of Z6. पॉज नहीं हो रहा है. Okay, next question, semigroup. You see the definition and I hope you will be able to solve this question. Next is on monoid. See the definition and solve it. Next question on homomorphism. Let me solve it for you. So what is a homomorphism? It is a function from one group to another group satisfying a certain property. So what is that property? Phi of A plus B equal to phi of A plus phi of B modulo n. So is this true? Can you verify that this property is satisfied? Let's discuss one simple example. Suppose n is equal to 6 and you are taking 4 and 5. So what will be phi of 4 plus 5? It will be phi of 9. What is phi of 9? 9 modulo 6. This is equal to 3. What is phi of 4? Phi of 4 is 4 modulo 6, which is 4. What is phi of 5? It is 5 modulo 6, which is 5. Next, what is phi of 4 plus modulo addition modulo 6, phi of 5? This is equal to 4 plus 5, which is equal to 9. What is 9 modulo 6? Again 3. So you see in both the case you are getting the same element. Hence phi of 4 plus 5 is same as phi of 5. 4 plus 5 is same as phi of 4 plus phi of 5. So this was just for your understanding. This is not the actual proof. You need to get the arbitrary element. So let A and B be the arbitrary element from the group Z. So what is phi of A plus B? This is A plus B mod n. What is phi of A plus phi of B with addition modulo n? This is A mod n plus B mod n. And we know it already that both these equations are exactly same. Hence, it is an homomorphism. Next example you see. This one. Is it an isomorphism? So for isomorphism, what do you require? First of all, it should be homomorphism, and second, it should be a bijective map. So first property you need to check is homomorphism. So what is phi of x plus y, where x and y are both real number? This is equal to exponential x plus y, which is equal to exponential x into exponential y. What is exponential s? What will be its preimage? Phi of x into what will be preimage of exponential y? Phi of y. So you see that the property of homomorphism is satisfied here. Next, is it bijective? For bijective, suppose phi of x is equal to x1 is equal to phi of x2. You need to show that x1 is equal to x2. If yes, then it is one function. So this is equal to exponential x1 equal to exponential x2. You can take exponential x1 minus x2 equal to 0 equal to 1. This will give you x1 minus x2 equal to 0. That implies x1 is equal to x2. Hence 1 1 Hence, this function is 1, 1. Next, you have to show onto function. You pick any number from right hand side. Suppose you pick y from R plus. You have to show that there exists an element in the domain such that phi of x is equal to y. So suppose that element is x, then phi of x is equal to y, and where should x be mapped? It should be mapped to exponential power x. Now from here, if you take log on both sides, what do you get? With base e, log y equal to x. So what do you get? X is equal to log y. So is log y a real number? Yes, it is a real number. Hence you have got the input, which is phi of log y. This is your input. This will give you y. Hence it is onto. So with this two property, it is bijective. With homomorphism included, it is an isomorphism. Next, we verify that Z plus and with this multiplication, it is a ring. We have already seen that with respect to plus, it is a abelian group, which if this question comes in exam, then you have to first show that it is an abelian group with respect to plus. Then with respect to dot, it is a semi group, which you can see that it is associative. N dot m, you multiply any two integer, then you multiply with the third integer. This is same as you multiply the integer n and then multiply with the multiplication of m, and both will give you the same result. So it is associative. Multiplication is closed, of course. So these two properties are satisfied. With respect to plus, it is abelian group. With respect to multiplication, it is semi group. Apart from this, multiplication is distributive over addition from both sides. That means n dot m plus p is same as n dot m plus n dot p, and m plus p dot n is same as m dot n plus p dot n. Hence, the first one is a. It is to be noted that in general, a ring may have identity or may not have multiplicative identity. In this case, it has multiplicative identity, which is 1. In the second example, you see 2z is also a ring, but it does not have multiplicative identity 1. Now, next question on field, is Z5 with respect to addition modulo 5 and multiplication modulo 5 is a field? That means you have to verify that with respect to plus, it is abelian group, which we have already seen. What about with respect to multiplication? It should again be a group. So what does this mean? It must have identity and inverse, apart from satisfying all the properties of ring. So with respect to addition modulo 5, we have already seen. Now let's see with respect to multiplication. So again, use the Cali table because it is your finite element. It is always better to use Cali table, and you need to put a star here. That means you are removing the additive identity from this element, and then you are looking for whether the remaining set is forming a group or not. So with respect to multiplication, you have 1, 2, 3, 4, 1, 2, 3, 4, 1 into 1, 1, 1 into 2, 2, 1 into 3, 3, 1 into 4, 4, 2 into 1, 2, 2 into 2, 4, 2 into 3, 6. What is 6 modulo 5? 1. 2 into 4, 8. What is 8 modulo 5? 3. 3 into 1, 3. 3 into 2, 6. 6 modulo 5 is 1. 3 into 3, 9. 9 modulo 5 is 4. 3 into 4, 12. 12 modulo 5 is 2. 4 into 1, 4. 4 into 2, 8. 8 modulo 5 is 3. 4 into 3, 12. 12 modulo 5 is 2. 4 into 4, 16. 16 modulo 5 is 1. So as you can see, all the elements belongs between 1 to 4. So closure property is definitely there. We have to only look for identity element and inverse. So if you see the row 1 or column, first row or first column, this is the identity element, because when you are performing with any integer, you are getting the same element. What about 2, 3, 4? For 2, when you multiply with 3, you are getting 1. That means 2 and 3, they are inverse of each other. What about 3? What about 4? 4 is inverse of itself. When you multiply 4 with 4, you are getting 1. So hence, it has identity element and every integer has got inverse. So this is the end of this revision session. Hope this is going to work well for you all, and practice well. Best of luck for your exam.